We have a few minutes, although, in fact, the coffee break is ready, for discussion of all the talks this morning. It was a very full morning, starting with this amazing talk by Reinhard Genzel, where he showed a huge amount of new data that I, at least, had never seen before. So any further questions for any of the speakers this morning, starting with Reinhard? Brant Robertson, I see, has a question.
This is for Reinhard. So the data was absolutely amazing. I was totally blown away by it. I did have a question about the fact that all the galaxies seem to be at J-disk equals 1, but then in the next slide you showed that they seem to be truncated. And that to me, just on the surface, seems perhaps inconsistent. Can you comment?
Repeat again. So at redshift...
If your disks are truncated,
Yeah.
they seem to be, that
Yeah.
they're falling off,
Right.
is that consistent with having the high angular momentum?
The J-disk equals 1.
Yeah, no, this is already included. So we have a correction factor in our calculating J-disk in there.
Okay, I actually have another question for you, Reinhard. So when you showed your plot with the line representing main sequence, and then the next line above and below a quarter or 4 times, they seem more or less uniformly distributed, whereas of course we expect them to be more concentrated. My guess is that you just, to avoid, you selected so as not to overplot so many. Yeah, okay, good. That's what I assumed you must have been doing, but you didn't say that. Yeah, okay. Good. So they have the normal distribution. Any other questions for any of the talks this morning?
I have one also.
Yes, okay.
So now there is some discussion about the sizes for Reinhard, about the sizes of the star-forming disks compared to the sizes of the already formed stellar components. So have you looked into the sizes of your H-alpha disks compared to the mass profiles that you showed?
Yeah, I mean, the best work on this is by Erika Nelson or Kate Whitaker on the 3D HST set. So if you look at Erika's paper on that, which is using basically narrowband information and stacking and so forth, you find it's a 10% effect. So on the high mass end, the gas disks are perhaps 10% larger, which is. Yeah. Mm-hmm.
Any further discussion? Excuse me.
I just wanted some clarification from Reinhard. You showed this plot where you had the specific angular momentum of the disk divided by that of the halo as a function of stellar mass. You didn't see any trend, consistent with simple expectations. And then you said, if I now pick out the ones that have very high surface density, they all lie low. And then you said, oh, compactification, radial inflow, instabilities. But isn't this exactly what you expect, even without any of those things mentioned, namely that low angular momentum systems will make more compact systems? It's sort of the standard prediction from the fall of Statue Moma white picture. So why did you suddenly infer all these complications? Isn't this exactly what you predict?
Well, the question is it nature or nurture? I mean, is it a process which was built in the lambda distribution? Okay, so if you can convince me that this is something which Andy and I in fact are discussing, but if you can convince me that this is nature, I'm happy to accept it. This was, I thought, an argument in favor of nurture. So it happens in the process as the galaxies grow along the main sequence, and then the process sets in, forming bulges and leading to dissipation.
Well, let me give another argument along the line of what Reinhard said, but he didn't actually say this, and that's the Barrow papers. So the idea is that at redshift 3, we see very few of these quenched compact objects. What we see is what we call blue nuggets, in other words, not quenched compact objects, and then there seems to be this trend of diffuse to compact, blue to compact quenched. And so if in fact at redshift 3 we could do a similar plot, which of course we can't yet, but then presumably what we would see is all the rotationally supported disks and not so much of these compact things. That would be a stronger argument. But indirectly, at least, I think the Barrow papers are already making that argument. Marcella?
Well, I just would like to add that I think it's in the same direction that Frank was mentioning, that when we make this statement, we must remember how the population grows, the evolution of the mass function. So, of course, we would expect less quench objects because the population is building up. So that doesn't answer, actually, the issue of nature versus nurture.
Sandy?
I'd like to make a similar comment to what Marcella just said. It's not as though we should compare those two populations. It's not as though necessarily the blue-green population evolved from the other population. And how galaxies get to this compact state by evolving through a two-dimensional diagram that is both mass and redshift, or mass and angular momentum, is more complicated. The models that were looked at by Avishai in Guillermo's first paper, in fact, somewhat evolve rather horizontally at fixed radius from small mass to large, and probably started out with smaller angular momentum just because they started out, relatively speaking, with low R.
On the other hand, simulations have some value, at least qualitatively. Yeah, no, not. On the other hand, to Frank. To Frank comment. So, yes, we should look at the observations and take them more seriously, but if we want to gain some wisdom when something is degenerate, we should go to a simulation. Compaction is a very, very robust phenomenon. It happens in all simulations, in almost every galaxy, so it must be there, and there's a real compaction event that's very, very strong. So we better try to interpret what we see consistently with what we learn from the simulations, or theory.
Just another comment on the observer side. I would say if you can find low mass, dense galaxies with low angular momentum, it would be proof that you can have some progenitors that are low mass and then they evolve with constant angular momentum, so they're very dense from the very beginning. I don't think we have seen a lot of those, but we can definitely search for them at the low mass end. On the other hand, you clearly see, and Ray has some beautiful images of that, you clearly see these galaxies grow in bulges, and you certainly do that by dissipation. So you expect some loss of angular momentum as well. So why not have both? I mean, I don't think it's inconsistent to having both processes. And as Avishai said, compaction is certainly working in the center of many of these massive galaxies.
Any further Reiner? Sorry, Roman.
So it's a different question, so I'm moving out. It's okay. So it's for Elad. So you mentioned at the very end of your talk the possible connection between the warm stream and the cool core versus non-cool core dichotomy. And so, I mean, I want maybe your reaction, but it seems to me that in your picture, relaxed clusters don't have deeply penetrated streams, while unrelaxed one have streams, warm streams, that bring in low entropy material to the center. But so, isn't it the opposite for the cool core, non-cool core picture? Observationally, I mean, it seems that cool core are, maybe I'm wrong, but cool core are in relaxed clusters, while non-cool core are, so that's the, so then it doesn't work with your warm filaments bringing in low entropy material, right? So
I don't think the streams themselves can actually solve the cool core problems by themselves. I don't think it's the streams. Thank you. I don't think it's the streams that are the sole reason for a cool core or non-cool core cluster. I certainly can't see them in the simulation, but I think that's more because of the limitations of this simulation. But generally, my opinion is that the streams might help solve the cool core problem in conjunction with the feedback from the AGN. I don't think the streams effect is that large that it can actually completely remove control the cool core versus non-cool core problem.
Okay, let's halt discussion now. Did you want to say something, Abhishek?
I think the women got it wrong, but we can talk about the coffee.
Okay, so let's talk over coffee, and let's come back. Let's aim to come back at 11:20. So just a short coffee break. Don't linger too much in front of the coffee or the pastries.